is a continuation of the Math 143 Semester 2 CWI practice packet. We're looking at question number 11. Solve by completing the square. Simplify your answer, write an exact answer, use radicals as needed, express complex numbers in terms of I. Remember, that's imaginary numbers. Complex numbers are imaginary numbers. And use a comma to separate answers as needed. This just gave us all kinds of hints. First, they told us to solve by completing the square, but I know there's many other methods besides completing the square, so let's just use whatever method is easier. It says to simplify answers, write exact answers. They say radicals. Those are roots. Radicals are roots, so that gives us a hint. Also talks about complex numbers with I. In other words, watch out, inside roots you could end up with imaginary numbers. So we should watch out for that. And use a comma to separate answers as needed. What? That means there could be more than one answer. So multiple answers. So they just gave us all kinds of hints here. Now this is a quadratic. So x squared plus 4x plus 5 equals 0. One method of solving is solving by completing the square. But actually, the first method I always like to try is just to try and factor this thing. So this actually can factor into, wait a minute, no it can't, because I'm thinking of what multiplies to make a 5 is a 5 and a 1, but they're both going to have to be positive in order to multiply to make positive and add together to make positive. And this doesn't factor right, so that didn't work. Now we could do completing the square, but another method is just to even graph it. So I'm going to go and graph it and see if that helps. I'm going to go to Desmos.com and graph this thing. I'm going to say y equals the x squared arrow over plus 4x and then plus the 5. Now, what I notice here, I'm going to expand this, is first, watch out for the scale. I have not adjusted the scale on their graph, but what I'm looking for are x-intercepts. And guess what? I don't see any. Although, you might be able to see them if you use your imagination. I'm thinking this is going to be imaginary because I can't see it cross the x-axis, but I think it would happen somewhere around here if I used my imagination. So I'm thinking that there are going to be imaginary answers, imaginary numbers. Now, how would we get that? And how would we even have roots? That's by using the quadratic formula. Now, I will say that while I wrote it, negative b plus or minus the square root of b squared minus 4ac all over 2a. I was worried that while I was whistling it, I was writing it down wrong. But there it is. So what do we need to do? We need to label what's a. A is the invisible 1 in front of there. What's b? B is the 4. And what's c? C is the 5. So I prefer to use quadratic formula as opposed to completing the square. This problem is actually pretty good for completing the square, but I'm just going to go with the good old trusty quadratic formula. So negative 4 plus or minus the square root of, well, what's b squared? What's 4 squared? That would be 16 minus 4 times the 1 times the 5 all over 2 times 1. So let's crunch this some more. Negative 4 plus or minus the square root of. Now we got to deal with the stuff in here. Here's where we got to watch out. Here's where you would get imaginary. If we get a negative under that square root in the end, then we got imaginary. So before we do that subtraction though, we got to do this multiplication. So first we have to do the correct order of operations. So I'm not going to do the 16 minus stuff. I got to figure out what that stuff is. That's going to be 20. If I multiply 4 times 1 times 5. Of course, I can multiply 2 times 1 pretty quick. Let's still keep calculating this stuff inside the root, inside the radical. So let's just copy down everything else. And that would be what? 16 minus 20 is negative 4. There we go. We just got a negative under the square root. It's the square root of negative 4. And what is the square root of negative 4? It's an imaginary thing. We should actually split that into a square root of negative 1 and then a square root of 4. We can multiply those back together to get square root of negative 4. But if we rip them apart, then we can see that that's the imaginary number, and that is the number 2. Really, I put them in the wrong order. Maybe I should have put the root 4 first, and then the square root of negative 1, because there's the normal 2, and this is the imaginary number I. So that would just be for this square root of negative 4. So I still have negative 4 plus or minus this imaginary thing that we figured out up here is 2i. And then it's all over the number 2. Now they also said in the instructions to simplify. That's just a fraction. I should be able to simplify that fraction because I actually have 2 things on top. That's a binomial. And so I really have negative 4 divided by the 2 plus or minus that 2i divided by the 2. Both of those things, all of that is divided by 2. Now if I do that, I can see that this first piece would become negative 2 plus or minus, and of course 2i divided by 2 is just 1i or I. There are my 2 answers. Remember, there could be multiple answers. My 2 answers are, if I sort of split them, it would be negative 2 plus I and negative 2 minus I. Those are my 2 answers. They say to separate them with a comma. So negative 2 plus I, comma, negative 2 minus I. That's my official answer. Of course, that's what x equals, so I'll scoop that into my answer. Let's try another one. In fact, same thing here. Again, we could probably just go right into it and just try and do quadratic formula. That might be the best way to jump into this one since that's how it worked last time. So what would be A? A would be 1, B would be negative 3, and C would be 7. The nice thing about quadratic formula is it's formulaic. It's great for like computer programming. You could just have that formula and your computer, you just plug in the correct numbers into the computer and it would just crunch it all for you. So negative 3, wait, what's negative 3? We'll deal with that in a minute. Plus or minus the square root of, well, what's, if b is negative 3, b squared would be negative 3 squared. Don't forget to wrap that in parentheses, or you should just know that negative 3 times negative 3 is going to come out positive 9. Minus 4 times a is 1, c is 7, all over 2 times 1. Okay. What was this whole negative 3? It was negative 3, which becomes positive 3. Plus or minus the square root of. Now, I'm going to ignore that stuff for a moment and just do the 2 times 1, because that's pretty easy. Because remember, our real focus in the end, we really got to worry about what's going on right in here. So that's going to be inside our root here. Remember order of operations. First we have to multiply 4 times 1 times 7, which is 28. And of course then we're going to do the 9 minus that 28. And then if I keep going here, plus or minus the square root of, I guess I don't need that positive 3. Now that it's positive, I know it's normal, so I'm going to get rid of that just because that's extra stuff. It's already busy enough. What is 9 minus 28? 9 minus 20, that's going to take me into the negatives. What is that? Is that negative 19? And there we go. Now, the square root of negative 19, that is definitely going to be imaginary. However, if I just ignore the negative for the moment, because that's what makes it imaginary, what if I just had square root of 19? Just like I tried to split earlier for the square root of negative 4, if I just thought over here for a moment about splitting the square root of 19 and the square root of negative 1. That's an I. But what about the square root of 19? I have no idea what the square root of 19 is. It is not nice. So I don't really go into there. I don't write it this way. I should bump the I in front. It should be I root 19. You don't want that, that I to look like it's still underneath the root because I can't really do much with that root. So I'm going to transfer this into, instead of the square root of negative 19, I would split the square root of negative 19 into this, but let's bump the I in front. I root 19 all over 2. Now there's really not much I can do to this. I could split it like I did in the problem before and have it 3 divided by the 2 and the I root 19 divided by 2, but there's really no point because I can't really simplify that fraction and I can't really simplify that fraction. So I'd prefer just to squeeze it back into one big old fraction. Don't forget, there are really two answers there. Remember, this hinted that there could be multiple answers. So if this really is sort of my answer, I could write it as two separate answers. 3 plus I root 19 over 2, comma, because they told me to use a comma. 3 minus I root 19 over 2. I really couldn't do much in terms of simplifying like they told me to do because there was nothing to simplify. So there we go. All right, this next one says solve the following inequality. Write your answer in interval notation, and of course use integers or fractions for any numbers in the expression. In other words, don't put crazy decimals if you end up doing some division. Just keep it like a fraction. Write an exact answer. Use radicals or roots if needed. Remember, radicals are just roots. So here we go. Here's the problem. Now, this is an inequality. I always like to think of these first as just a good old equality. What if I had this? Well, that's a whole lot like the problem we just did up there. We just did one that had an equal sign, just like that. So we could do the same sort of thing. We could do quadratic formula, we could try and factor, we could graph, we could even complete the square, although I didn't earlier, even though it told me to. So let's see what we got. Now this one, I actually noticed something here. Just like before, I tried to factor right away. I would try and factor right away because I'm noticing that this one, to make the x squared, could be an x and an x. What could make a 15? What could multiply to make the numbers on the end of a 15? It could be a 1 and a 15. It could be a 3 and a 5. It could be a 5 and a 3, but that's a duplicate. So I found all the options. And I like this one because a 3 and a 5 could make 8. Problem is we need some negativeness. Watch this. A negative 3 and a negative 5 could multiply to make positive 15. And a negative 3 plus a negative 5 could add to make negative 8. So that is the correct factorization, is using x minus 3 and x minus 5. Of course, you can put it in the different order. Doesn't matter when we're multiplying these packages, these binomial factors. So here we go. I got the factorization. Now I could just solve what makes this piece equal 0. That's when it's positive 3. What would make this piece equal 0? That's when it's positive 5. I just found the two answers. So that would be x equals 3 and x equals 5. Oh, but wait a minute. I was about to put my answer when I noticed write your answer in interval notation. Wait, this is when it exactly equals 0. We don't want to know just when it equals 0. This says when is this thing less than or equal to 0. What I need to do is make a sign line. So we have 3 as a 0. That makes it equal 0. In fact, I want it to equal 0, so I'm going to put a solid dot there. That's a good spot. As well as 5. That's a solid spot. What I could do is I could test these 3 different regions. I'm actually going to test in the middle because I actually know that when it's talking about less than or equal to 0 for this parabola thing, this quadratic, it's actually going to be this middle spot because that's when it dips down or less than 0. Watch what I mean. Let me test out the number 4, which is right here somewhere in the middle. In fact, it's actually perfectly in the middle. If I plug this into the original problem, that would be 4 squared minus 8 times 4 plus 15. Is that less than or equal to 0? We'll find out. 4 squared is 16. Minus 8 times 4 is what? 32. Plus 15. Is that less than or equal to 0? I'll put a question mark here. Is it? I don't know. I do know that this positiveness plus this positiveness together make 31. And then if I subtract 32 from that, well, that would give me negative 1. And is that less than or equal to 0? Yes. So this was the good spot, which means I want to connect those two dots because all the stuff in here is good. These two dots are good because they make it equal 0, which is what I want, equal to 0 here, as well as this is the space in here, which would make it less. Of course, if you tested over here, you would see that it would be, oops, wrong button. You would see that that would be bad. And if you tested over here, you would see that that would be bad. So our solution is right in here. We need to write that answer in interval notation. If you remember that interval notation starts here at 3 as a good spot, so I use a bracket, comma, and then it ends at this far side, the upper limit, and that's also a good spot, so the 5 is also going to be in a bracket. There is my interval notation. What I'm going to do is I'm going to even sort of check this in a way. I'm going to graph this thing using Desmos. So let me get rid of the other parabola we had earlier. In fact, let me just kind of rewrite this one. We're going to have the x squared minus 8x plus 15. And if I go and look at this, while I have my work over here showing, I can actually see something kind of important. I see the answer of 3 here and 5 there, and I notice that the parabola dips below. In fact, let me scroll over this way so I can see the question. I want to know when this parabola is less than or equal to 0. And I can see that here are the zeros, or the x-intercepts, and this dips down. In other words, it's less than the 0. These are negative y values. So I can see that that middle is my answer, between 3 and 5. And so there we go, between 3 and 5, and we see it here, between 3 and 5. Let's use that technique of graphing. Let's see if that can help speed up this last problem, or this problem number 14 right here. So let's graph this thing. Let's see, it's what, plus 3x and minus 70? Hole mole. So I'm going to expand this to see. In fact, maybe I can shrink this down a little bit and zoom in. My parabola, actually I'm zooming out, my parabola looks huge. I can't even see how far down it goes. It goes way down there and then comes back up. But it looks like it crosses at, what is that, 7? And it crosses at negative 10. So if I were to just draw a rough sketch of this over here, it looks like it crossed, what did it crossed at 7 and it crossed at negative 10. And it went like way down here or something crazy. So, when is this going to be not equal to 0, but just greater than 0? Well, remember, these x-intercepts are the zeros. Now, when is it greater than those zeros? Well, earlier, this dip down here was when it was less than the 0. So we want stuff that's greater than 0. Over here, shooting up is going to be greater than 0. And in fact, it's going to keep going up on that left side, on the left end. And on this right end, it's also going to be greater than 0 as it keeps going up forever. So we just found the two places, and we just need to write our answer in interval notation here. So how do we get that left side? Well, it's going to be going forever out to infinity. So that means interval notation starts on the far left. It's going to go negative infinity. We don't put a bracket because that would be equal, and you don't ever equal infinity. Now, we could get out to 10 and negative 10. Now, if I put a bracket here, that would be good if I actually wanted to equal that spot. But you know what? Since this says not equal to, I actually don't want, oops, that just erased almost everything. I actually don't want that spot. I would want an open dot there. So I don't want a bracket. I actually want a parentheses because I don't want to equal that. Same thing over here. I don't want to equal that spot, so I put an open dot. And so I'm going to put an open bracket, and I'm going to put 7. And it's going to go out to positive infinity. And of course, we never equal infinity, so I use the parentheses. Now, it could be either one of these answers. And in interval notation, CWI likes to use the union symbol, the U there, meaning union. It really just means or. You can have this stuff, or you could have that stuff. We could join those two possibilities into one big old possibility. This one says graph the system of inequalities. Then find the coordinates of the point of intersection. So I'm just going to do a rough graph, and then I'm going to actually use a graphing calculator to help me out. So this first one, this first equation, you should know that as a circle. The circle has a radius of, oh wait, that's the radius in disguise. I don't know what the square root of 13 is. It's going to be less than 4, greater than 3, so 3 point something. So it's some kind of radius of circle of 3 point something. Pretend that's a circle. And of course, it says less than, which means technically I would want to shade inside because I want to be less than that radius. I want to be inside that radius. So there's my first guy. Now technically, it should be a dashed circle because we don't actually want to equal. See if I can erase just that. Good, I got it. We don't actually want to equal the radius of 13, we want to just be less than. So this one actually needs to be a dashed circle. And then this other one, this other guy is a line actually. There's a couple ways to graph it. Is I could actually subtract that x over, and it would say y is greater than or equal to the negative x that I subtracted over, plus that 1 that's already there. So that would be a line that starts here at 1 on the y-axis and actually has a slope of -1. And so, you know, it'd like go down something like this. Now this one actually has an equal sign, so I actually can draw a solid line because it has that equal there. Now what about shading? This says y needs to be greater than or equal to this line. So that would actually be above. So I'm going to shade everywhere above the line. Everywhere above the line. Now we have the blue shading and the yellow shading. And you notice where those two things mix together, yellow and blue makes green. So what we've got, and of course this actually keeps going forever, but I'm not going to do that forever. We're looking for where this system works together. Remember, a system is something that functions together. So we want to know when these two things are together, the yellow and the blue. And it looks like it's right in that space. So that is the important stuff. Okay, that's sort of the solution. So I graph the system. This is then find the coordinates of the points of intersection. So I need to know where does this line hit that circle and where does the line hit that circle. There's some fancy algebra you can do, but as a skill with technology, it's important to be able to use our technology. So I'm going to go and I'm actually going to type in these two things. It actually doesn't matter to me if I put the less than or not. That's actually not my focus. I'll put the less than just so I can see it. So there's my circle. And then let's also do the x plus y is greater than or equal to. Notice for the circle it was dashed. If I do greater than or equal to 1, notice that did a solid line. They used different colors than I did, but the real important thing is I'm looking for is where they intersect. Now I can actually click on them and find that important intersection point. It looks like it crosses at 3, -2, and it looks like it crosses at -2, 3. So 3, -2, and -2, 3. I'm going to write those down on here. So that was the point 3, -2, and this was the point -2, 3. Those were the two intersection points. It looks like I should list them here. 3, -2, comma, because it told me to use a comma, -2, 3. It says write the ordered pair. So there is my answer for this. Let's do this other one here, a whole lot like it. Graph the system of inequalities and find the coordinates. Again, looks like I got another circle here, although this one looks like it has a nice radius. So let me just sketch a quick graph. Looks like the radius is 5. So let's just pretend that's 5 and 5, 5. Of course, -5 on these ones. And it's actually going to be a solid circle this time. Again, pretend it's a circle. Be nice. It's hard to do this on the computer. And this one says that this circle, this x squared plus y squared, is greater than or equal to that radius, which means it's actually going to be shaded on the outside. I don't want to be in the circle. I don't want to be inside that, closer. I want to be farther away or greater away. So something like that. Pretend. Of course, it goes forever, but I'm not going to color in forever. Then for the line, again, I'm going to move this into y equals mx plus b form. I'm going to go y is less than or equal to, and then I'm going to subtract that over. And then I have the plus 1. So again, this has a y-intercept of 1, and the slope goes down 1 over 1, down 1 over 1, and so on. And this one is actually not equal to, so I should keep drawing these dots as like dotted lines. And this one says y is less than that -x plus 1. So I want y values that are below the line, less than or below. Now notice inside the circle is blue, but outside the circle is turning green because that's where I shaded outside the circle. So I really want the shading, the ultimate answer is all the stuff out here that's both of them. It also includes that border of the circle because the circle is equal to, which means it's good space. Now what I really care about is finding the coordinates of the point of intersection. Like, where is that? Again, I'm going to go to the technology, and I'm going to use the technology to help me find that, the tool of graphing. So, of course, I could just graph this whole thing for real by using the inequalities. But to be honest, it doesn't really matter because all I really want to do is find out where they meet. So I could even just use an equal sign here. There we go. So where do these two meet? Looks like these two meet at 4, -3 and -3, 4. So 4, -3, that's this one, and -3, 4. Notice because of circles, just like the problem before, it seemed to have some symmetry also because of the way that line was a nice steady line there. It gave some symmetry on the points of intersection. By symmetry, it's not exactly symmetrical, but notice it has this evenness as to the up and down or the left and right, even though stuff switched a little bit. So there we go. That's how we can solve that one.